The first part of the rule is always that we are dealing with real numbers. But then we also have another restriction. Out of all those infinite x's, I may put a semicolon or the word and, okay? Because another rule is that x cannot be 2.
What if you write it like exactly like that, but instead of having the all real numbers, you put like negative infinity is less than 2 and greater than?
Exactly, in interval notation, right?
Yeah.
Yes. So just like up here with polynomials, either in set builder notation or interval notation, I want you to recognize both. MATLAB on this homework assignment is going to ask for set builder notation. But I want you to recognize both. That means that it goes from, interval notation means smallest, commas, greatest. The smallest possible version, smallest possible value of x is negative infinity, and it goes all the way up to the biggest possible value, which is positive infinity with no breaks in between. Okay? Set builder says it's just all real numbers. Here it says it's all real numbers except for this one. In interval notation, yeah. So this is set builder. Okay. But in interval notation, what is the smallest possible value that x can be here?
Negative infinity.
Right. And imagine yourself on the number line. You're starting the smallest, negative infinity. You go up into where?
2.
You hit it, yeah. At 2, you've got your asymptote. So you go up to 2. 2 is not included, right? Soft parenthesis. We got to make a little jump because everything up to 2 and after 2 is included. So we just make a really small jump. We pick up again on the other side of 2. The soft parenthesis means 2 is not included, so it's just a little bitty jump. And then we go to the biggest possible value, and we close it.
When I was in pre-cal last year, our teacher taught us like in the x this set of x way, but you also put like I wrote it down right here.
Let me see.
That's what I was talking about. Like whenever you write it like that.
Oh, okay. All right, yeah, that's another way. Yeah, so x is a member of. That's kind of mixing up set builder with interval.
Yeah.
I think that's a little awkward, but it's not wrong. And so if that works for you,
I was wondering if that was right with you. So.
Yeah. See, the thing about set builder notation is there's not always one right way. For example, in MATLAB, they're not going to use this notation. They're going to say x is a real number. They're going to spell it out in words. Okay? And there's other ways to write your rules. You could literally write x cannot be 2. You can write it out in words. Or you put it as x is in between, what was it?
I put negative infinity is less than 2, and 2 is less than infinity. So it shows that it can't. You know what I mean?
Okay, yeah.
But I was just wondering.
Yeah, I think this is a little cleaner to do it this way, and this is why MATLAB is going to ask you, so this is how I'd like to see it.
Yeah.
But there are other ways. With set builder notation, you have to convey what the rule is.
Yeah.
And there's ways you can say that in different words or different symbols. Mm-hmm. So there might be more than one way to convey that rule. Okay. Yeah. Okay. Good. Other questions? Okay. All right. But this is pure set builder, and this is pure interval notation. Yeah, what you should kind of put them together a little bit. Yeah. Okay. All right. So let's look at some functions and how we write both their restrictions and their domains, and also how we evaluate. All right. So. All right. So we looked at let me make something really clear here. So I want to make clear about when we're at, before we move on to evaluating. Let me make real clear, too, about two different things. On this one right here, if you were asked for the restrictions, okay, so the restrictions means x cannot be, okay. Then in this case, the restriction of this case is that x cannot be 2. Okay? So that's the restriction. That's saying what x cannot be. And that's different from saying that it uses the same idea, but the domain is saying what x can be.
So it can be x in between.
Right. So the restriction says what x can't be, and the domain, on the other hand, says what x can be. And to find the domain, you first have to find the restriction. If you're just asked for the restriction, you say, oh, it can't be 2. But if you're asked for the domain, you find what the restriction is, and then you write it in either set builder or interval notation, depending on what you're asked for. So x So in this case, x can be a real number. The domain is x can be a real number as long as x is not 2. Your restriction is part of your domain. But the whole point of the domain is saying what x can be. X can be any real number except for that one. Okay? So be careful when you're looking at my math lab or on the test. Am I asking for the restriction and you just tell me what x can't be, or am I asking for the domain? And if that's the case, you have to find the restriction and then tell me all the x's it can be by using either interval or set builder notation. Okay? So just a little vocabulary note there. Okay? Good? Okay. All right. So another thing we can do is we can evaluate a function. And we've already been evaluating functions. You already know how to evaluate a polynomial function. So I'm mostly just going to show you a couple of tips you need to know to make sure and keep it straight, because when you use your either mentally or on paper or use your calculator, how to make sure that you are evaluating it in an organized way so you don't lose track of where the number should go. So let's go ahead and still use that f of x is equal to 3 plus x over x minus 2. And evaluate means, well, I'm not solving that. I mean, I could graph this, okay? Or you're going to evaluate a function, or you might just be evaluating an expression. Either way, you're not solving it. You're just being told, hey, what if x equals something? And you plug in the x and you see what the value is if x were that, okay? So if you evaluate this, if x equals 4, then since I gave you a function, what you're evaluating is f of 4. Okay. And so f of 4 means everywhere I see an x, and remember, always put it in parentheses. Okay. It may seem like overkill for basic small positive numbers, but when you're dealing with fractions and negative numbers, it keeps things clear, and it also helps you enter it in the calculator properly. So f of 4, this is the general function that would make an infinite graph, but we're looking for a specific point on that graph. If x is 4, what is y? 7. Right, so we have 3 plus 4 over x minus 4. You plug in 4 everywhere you see x. And then simplify, and this one can be simplified manually pretty easily. We've got 7 on top, and on the bottom we have, oh, I'm sorry. That is, way off there, yes. It's 4 minus 2, yeah. So, of course, x minus 2 means 4 minus 2. There we go. And that gives us 7 on top and 2 on the bottom. Okay. So, f of 4 is equal to 7/2. In this function that can be graphed, an infinite graph, what is one point that is on that graph?
7 over 2.
Yeah. Well, the point, an ordered pair, what's our x value? And if x is 4, what's our y value?
7.
Yeah. That's what a function does. It's a little machine. You plug in an x, it spits out a y. And you can do that again and again and again and get infinite ordered pairs, x comma y, which define a graph. You connect the dots, you have a graph. And this is one of those infinite points on that graph. Okay, so you can evaluate a function at any value of x that you're given. Now you need to be careful when you are playing. Let's say we have that same function, f of x is equal to 3 plus x over x minus 2. And let's say if x equals negative 8. Now again, I'm going to plug in, so f of negative 8 would equal 3 plus negative 8. Always plug it in parentheses. And over negative 8, keep doing that, negative 8 minus 2. Now again, hopefully you can still do that one pencil and paper, but I'm going to show you 2 different ways to enter it in the calculator. Because as you get more and more complex, because this is 2 linear polynomials as part of this rational, but when you get into more exponents and things, you're going to want to use the calculator. Okay? Now you can just enter it just as you see it. So I'd first plug it in parentheses and enter it just like that in the calculator. But remember when we entered this to be graphed, the numerator and the denominator each had to have their own set of parentheses. It's the same thing when you're evaluating. If you don't do that, then the calculator is going to mess up the order of operations. Because order of operations, when you have a rational bar, means do everything on top separately and everything on the bottom separately, and then you'll do any sort of division or simplification interaction. And so if you don't tell the calculator, deal with this separately and that separately, it's going to mess it up. Okay? So you're going to need to put, besides putting in your x equals -8 in parentheses, you need to put parentheses around the numerator and the denominator. So we're doing nested parentheses. Nested means parentheses inside of parentheses. Now I put it as brackets just for clarity there. There are no brackets on here. It'll just be parentheses inside of parentheses. So to enter that into the calculator, we would do, just like we see it there, open the parenthesis for the numerator, put in 3 plus, and then I'm plugging in -8 for x, so it would be parenthesis -8, close the parenthesis, and then close the numerator parenthesis. So 3 plus -8 inside numerator parentheses. Make sense? Now we do our division bar, our quotient bar there, our rational bar. And now open up your denominator parentheses. And now we plug in our -8, so parenthesis -8, close that parenthesis, minus 2, and now close your denominator parenthesis. Now remember, many times you're going to get back a decimal answer. Your answer should be as an integer or a lowest term fraction. So if you get back a decimal answer, remember it's just math, enter,
1/2.
And it'll change it to a fraction.
But you don't have to do it the way that you did it, because if you do 3 minus -8, you're still going to get -5 over 10.
Right, and you put it low. Yes, if you do it manually, yes. I'm just showing the calculator skills because you will get a lot more complicated and we'll need them. So if you've got, for example, exponents involved and everything, you're gonna want to use this to help. Now to make it even cleaner would be to use that store button again. This is where that store button really gets important because it really keeps it cleaner. So, but still, you will still need to tell the calculator numerator / denominator. So instead of physically entering -8 in its own set of parentheses, a cleaner way to do it is to use the store button. Tell the calculator that you want x to be -8. So put in -8, store, which is above the on key, down the bottom left, and it's going to say, where do you want me to put it? Push the X button up here under mode, and push enter. And the calculator says, okay. If you entered a fraction, it's going to turn into a decimal, no worries. Push enter, and now anytime you put in x, it's going to know you mean -8. And so you don't need to put x in parentheses now. You just write exactly what you see, except you have to lock up your numerator and your denominator to help the calculator know order of operations. So it'd be parenthesis 3 plus x, close parentheses, there's my numerator, rational bar, denominator parenthesis, so parenthesis x minus 2, close the denominator parenthesis. Much cleaner to enter it, but you still need numerator parenthesis, denominator parenthesis. And the calculator will then substitute -8 in for x, giving you 0.5, math, enter, gives you the lowest term fraction. So your challenge on homework is you'll have ones like this, but there will also be exponents involved. You'll have,
Can you do the store thing again?
yeah, so if I wanted to put in -8, you put in what you want to store first. So I put in -8. And store button is above the on key in the bottom left.
Okay.
Yeah. And when you push that, you'll get an arrow because the calculator is saying, where do you want me to put it? And you're just in general put in X. We can put any letter you want, but just for our purposes, all you need is an X, which is right there. And you push enter to acknowledge. Please store -8 in X. And it says, okay, that's done. And you don't have to erase it later. It's just going to stay -8 until you write over it, until you tell it to store something different. And then it will replace the -8 with whatever else you choose. Okay, so you don't ever have to erase what's stored. And of course, if you do that, it's a lot cleaner, especially when you got exponents involved in your polynomials as well. Okay? So you'll try those on homework, and if you have any sort of calculator issues on how to enter it, let me know, and we'll work through it in the next class as well, or send me an email. Okay, so that is evaluating a function. Okay, you're given an x. Just make sure you plug it in very cleanly, and since you're dealing with rationals, your numerator and denominator to be locked up separately. Whether you're doing it manually, or whether you're entering it manually into the calculator, or whether you're using the store button, you still have to enter numerator / denominator in parentheses. Each one in parentheses. Okay, so let's find some domains of various rational functions. So if we've got a function of x squared plus 2 over 3x plus 4. I'm going to put a few of these up here, and then we'll work through them. And then we've got, let's see, x equals 8x cubed plus 7x squared plus 20 over 2. Now, when we're finding domains, when you're asked to find the domain of this function, all that matters is the denominator. The numerator doesn't make any difference. The numerator can be 0 or positive or negative. It makes no difference. Those are real and defined numbers. It's only the denominator that's a problem. Now, you're going to, all you want to know is, it's not that x is 0. You want to know what makes the denominator 0. So you're going to be solving. You take your denominator, and you set it equal to 0. And you're going to solve it just like an equation. But you'll see me do this, actually, because though you solve it like an equation, I want to be really clear that what you're trying to find out is what x cannot equal. Okay? So I set my denominator not equal to 0, meaning I have to find the x, what x cannot be. And my denominator, this means my denominator cannot equal 0. Because then I would have an undefined function. Okay. Now, my denominator, if I solve this little equation, what kind of equation is this? Linear, right. So I'm going to get how many solutions? 1. So how many, in this case, how many restrictions am I going to have? 1. Yeah. So if I have a linear denominator, then that means I'm going to have 1 restriction. Okay. The degree of your denominator, just like the degree of any equation tells you how many solutions you'll get, the degree of your denominator, since you're going to solve it like an equation, is going to tell you how many restrictions you'll get. Okay. So when you solve this, you get 3x equals negative 4, so x equals negative 4/3. Or rather, cannot equal negative 4/3. You solve it just like you were solving 3x plus 4 equals 0, but I use the not equal to because even though we're solving it just like an equation, what we're trying to find out is what x can't be. And this is our restriction. Out of all the possible x's, that's the one thing x cannot be. Make sense? Now, let's write it in a positive way. Let's say what x can be. Let's write our domain. And our domain means x can be anything as long as it follows the following rule. First, it must be a real number. Also, even though it can be anything, there's one restriction: it cannot be negative 4/3. So when you're asked to find the domain of a rational, look at its denominator, and only its denominator. The degree of that denominator will tell you how many restrictions there are. You set that denominator equal to 0, or to not equal 0, because when you solve it just like an equation, you're going to find out what x can't be. And then that restriction is part of your domain, because x can be anything except that. And then another little bonus understanding here is that x equals negative 4/3 is what? When you have x equals a number, you have what on a graph? A vertical line. Now that's not part of this graph, but x equals negative 4/3 tells us that dashed vertical line, which we call the
Asymptote.
Right. So this is the vertical, x equals negative 4/3 is the vertical asymptote. As part of the domain, x as part of the domain, as in all the possible x's in ordered pairs, you will never find an ordered pair where x is equal to negative 4/3. So x cannot be negative 4/3. But if you write it as x equals negative 4/3, what you wrote is the vertical asymptote. The equation of the vertical asymptote. Which if you drew it on your graph, you would draw it in as a dashed line because it's not part of the function. It shows you what the function will never be. Will never touch. Make sense? The differences between those, the vocabulary? Okay, so let's move forward. So, what is the degree of this denominator? That's the number, but what's its degree? Well, first degree would be linear. That means it has an x.
4. 4.
Okay. Degree 1 is linear. That means there's an x with an exponent of 1. This is just a constant, right? What's less than 1? 0. Constants are degree 0. Because there is an x there, but it's an x with an exponent of 0. Because an exponent of 0 means you have x to the exponent of 0, x raised to the 0 power equals 1. Anything raised to the 0 power equals 1. So you could say this is 2x to the 0 power, because that would be 2 times 1. So there is an x here with an exponent of 0, and that exponent tells you the degree. But anything raised to the 0 power equals 1, so this would be 2 times 1. That's getting really technical mathematical definition of it. But if you have just a plain x, it has an exponent of 1, therefore it is linear. It's degree 1, which is linear, 1 restriction. If you just have a constant, that's degree 0. How many restrictions will you have? None, right. No restrictions. Yeah. Because think of it this way. What x, you plug in any x. Is there any x you could plug in? Can you imagine any x in the world you could plug in that's going to make this denominator equal 0?
No.
How can it? If there's no x there, then nothing's going to turn that 2 into a 0. So if there's no x in the denominator, nothing will ever make it 0. Okay. Does that make sense?
So it would be undefined?
Oh no, it's defined everywhere. This is actually a polynomial because you can divide 2 into here, here, and here, and you'll actually have a nice flat polynomial. This is actually a cubic. If you have and so it's defined everywhere. It doesn't have any restrictions.
Okay.
There's nothing you could plug in for x that would make this undefined. That's the answer. So your domain, there's no restrictions, and your domain is just x such that x is a real number. Okay. Or in interval notation.
So when you call it constant,
Mhm.
there would be no restrictions.
Yeah. There's nothing that would make nothing that would make that denominator undefined.
Even negative.
Yeah, because if your x, whatever x is, you're plugging in it up here, but there's nowhere to plug it in down here, so nothing could turn 2 into something else. If you have no variable, you're not going to change the value of something. There's no variable here, so there's nothing that will make it change its value. It's 2, constantly 2. That's why it's called a constant.
Do you want us to write both those answers?
It depends on what you're asked for. If you're asked for restrictions, you'll say no restrictions. If you're asked for the domain, then I want you to answer in set builder notation, or interval, depending on what you're asked for.
Oh.
Yeah. And Math Lab's going to ask for the interval. I'm sorry, for the set builder. So I want you to get used to that. Okay, so here, what is the degree of our denominator?
1.
Yeah, it's a linear denominator. Okay. So that is first degree, or degree 1. Okay. So how many restrictions will we have?
1.
Yeah, 1 restriction. So take your denominator, set it equal to, or rather not equal to 0, because we're trying to find out what x can't be. Okay. Solve it. So x cannot be,
0.
right, just divide both sides by 4. Doesn't matter what you're dividing by, it still equals 0. So that is our restriction. And so our domain is x such that x is a real number, but also x cannot be 0. Now, if you wanted to write this in interval notation, or you were asked to, what's the smallest value x can be?
Smallest x.
Yeah, what's the smallest x possible here?
Is it a negative infinity?
Right, yeah. Anything. It's infinite, so negative infinity, but we move along that number line from negative infinity, and when we get to 0, we hit a wall. We have to jump over 0, pick back up on the other side, and go to infinity. Remember, this goes from least to greatest, but everywhere you have a jump means you have an asymptote. Okay, you have a break. You have a restriction. Okay, so and when you write an interval notation, that shows you jump here, restriction, restriction, restriction. There's one restriction here, so there's one U, one gap, one jump. You could say your vertical asymptote is x equals 0. That would be the vertical line, dashed vertical line that goes through 0 on the x-axis. Okay? Or in other words, the y-axis. Another word for the y-axis is x equals 0. So this graph will never touch the y-axis. How many, what degree is this denominator?
Second.
Third.
Okay. Yeah, third, so we got a cubic. The cubic denominator, so that's degree 3, so how many restrictions?
3.
Take that denominator, set it not equal to 0. Now, what we've had so far has been linear. If we had anything, they've been linear. And we just solve the linear equations by adding the same thing to both sides, or subtracting the same thing to both sides, dividing away our coefficient. Okay, so our linear rules for solving linear equations. But this is a higher degree polynomial equation. How do we solve that? Well, we just wrote the denominator, so it's polynomial. Right? That's the start. We're going to solve it by factoring. This is what we just took the test on. Right? So this is where that skill comes in. We're solving it just like any other polynomial equation. Our first thought is, can we factor it? And the first thing we do when we factor is GCF. And there is one. We take out an x. Now, we're not done until everything is linear. How many factors are we expecting? Because each one's going to give us a solution, or in this case, each one's going to give us a restriction.
Linear factoring.
Yeah? So we continue factoring, and this factors into?
X minus 9.
Difference of squares. As long as it still has an exponent, you think, oh, am I done yet? Maybe you will be if it's prime, but for our case right now, you're going to be able to factor all the way down to linear. So you should have 3 linear factors, and so x cannot equal 0. X plus 9 cannot equal 0, so x cannot equal negative 9. And x minus 9 cannot equal 0, so x cannot equal positive 9. There's your 3 restrictions, just as if you were solving for your 3 solutions.
Okay, might be getting ahead of myself.
Okay, go on.
But it's, so when you multiply the equation times 1, that's when you're simplifying.
When you multiply the equation times 1.
Yes.
I'm not sure.
Okay, just keep going.
Okay.
Just keep going.
Okay. Hold that thought. Let me look at, yeah. All right, so you've got 3 restrictions. How many